Okay, so as I say, I'm going to be presenting some work from myself and my co-author, Dr. Leon Dwan. So what we did is we varied the time step sizing for the DrivAer notchback model, and then we went through and did some uncertainty quantification of the flow field for this. So just a quick overview of this presentation. I'm going to go over our motivation behind this, our simulation setup, and then for the results, we're going to talk about the convergence of the drag coefficient, variation of the drag and lift coefficients, design trends, and then go into the flow field, and then the design trends for the flow field before wrapping up with the key takeaways and future work. So for our motivation, as we've seen, unstay methods are more accurate than RANDs. This has been established in every AutoCFD workshop thus far. Now, time stepping, though, leads to increased cost, but we can mitigate this by using larger time step sizes. But this introduces some potential sources of error. So you have statistical error due to the fact that we have fewer samples with larger time step sizes. And then we also have some numerical error, so decreased temporal resolution with larger time step sizes. And then the convergence of time steps through inner iterations. You need more iterations for these larger time step sizes. So this gives us a question here: how to balance the cost, accuracy or consistency, and the uncertainty with respect to time step size and the iterations per time step size. So we just focused on case 2A and 2B using star CCM+. We used DDES with a turbulence model of K omega SST. And then for our time stepping, we used the implicit second order method. And so we have several time step sizes, and these correspond to CFL equals 1, which is temporally over-resolved because the Courant Friedrichs-Lewis condition is, of course, set to explicit methods. It does not take advantage of the stability of implicit methods. We also use a CFL equals 10, which is sufficiently resolved for mean flow, as has been shown through the literature. And then finally, we also use a CFL of 100. This is temporally under-resolved, but the reason we want to do this is we are engineers, so we want to see, can we still get a good design trend out of this temporally under-resolved, even if we don't expect it to match CFL of 1. So this gives us our full setup here. So for CFL 1, 10, and 100, we have a time step size of 2.6 times 10 to the minus 5th, minus 4th, and minus 3rd seconds. We used a washout time of 0.6 seconds, which is a convective time of 5, then a 2.7 second averaging window, and that's a convective time of 22.8 convective times. So now for time step convergence. I would say the number of inner iterations is something that to me is not physically meaningful. Reason being, this is not likely to transfer between vehicles and speeds if I say I need 5 iterations per time step. So what we decided to do was, we consider this uncertainty quantification of inner iterations. If you consider, the drag coefficient and the last 2 iterations for a given time step, there's kind of a question here. What happens if for one time step, the difference between those iterations is, say, 2 counts, and then at the next time step, it's half a count? How does that uncertainty start to impact your transient solution and the subsequent statistics? So we allowed our inner iterations to float in this case, and we compared the current and previous iterations, and then we based our convergence off of lift and drag, so delta CF. And in this case, we took the difference between those last 2 iterations and set that to some value theta. And we limited this to 2 iterations and then a maximum of 20, 2 because obviously we need 2 iterations to do this comparison, and then 20 because this gets kind of expensive. So this gave us our nice test matrix here, our 3 CFL numbers, and then we base this off of the counts of lift and drag. So delta CF equals 0.01 counts, 0.1 counts, and then finally 1 count. So taking a look at our drag coefficient, if we took our uncertainty with respect to our averaging window as we got out of mean calc in this case, we see we get similar uncertainty regardless of time step or convergence. In this case, it varied from about half a count to 2 counts. We did note that for all of these trends, there was no monotonic trend for either time step size or convergence here, so nothing clean there. But we do note that we have the same general trend in convergence. As noted before, there's a constant rate of decay for all of these, so it's just a shift in the trend. So our key takeaway is that the uncertainty drag is dependent on that initial value of uncertainty, and you can then actually predict how long your simulation needs to run based off that initial uncertainty value, and then what value you're targeting. So going through and comparing this now and seeing our variation in lift and drag as we change our time step size and convergence. Our variation with convergence, so looking at just CFL equals 1, there's approximately a 1 count difference in both drag and lift. And this aligns closely with our uncertainty estimate epsilon. Going to CFL equals 10, it's 5 counts and 9 for drag and lift. And then CFL of 100, it's 6 and 6. So the key takeaway here is that there's a sensitivity to inner iterations that seems to be increasing with time step size. This is something that's been established in the literature. But the big thing here is that smaller time step sizes with fewer inner iterations seem to be a better match for our best resolved case, that delta CF equals 0.01 for CFL equals 1. So now how does this compare when we start doing the design trends? So in this case, we took an A minus B design trend, which is quite literally the difference between case 2A and 2B. What we see is the difference in our drag trends from our best resolved case, so the delta value. We found that that was within the uncertainty bounds for CFL equals 1 and 10, and delta CF equals 0.01 and 0.1 counts. Now the lift trends, though, they're consistently outside those uncertainty bounds when we take a look at it. But the key thing is those 4 cases, again, 1 and 10 and delta CF of 0.01 and 0.1 counts, at least produce the same design trend. We get the same negative sign in our delta CL value. So our key takeaway here is for design trends, the time step size can actually be relaxed a bit as long as we go through and utilize more inner iterations. So now, how does all of this go through and affect our flow field? So we took the difference in our average velocity magnitude for CFL equals 1 with differing convergence criteria. So we have CF equals 0.1, minus 0.01 up top, and then 1 count minus 0.01 counts of convergence for the bottom there. What we see naturally is that our largest differences occur in the separated flow, in the underbody geometry, and in the wake. Now, we do note that these differences are actually larger than differences we saw for our averaging window. So in this case, there's a maximum difference of 8 to 10% of the free stream versus 2% if we took the difference over the last 5 convective times, and it was about 3 to 4% for the last 10 convective times for increasing our averaging window. We do note that there is a massive difference near the ground in the wake for delta CF equals 0.1 counts. This was likely due to a numerical issue that we saw. We had a really hard time getting this one to converge. So for this one particular case, we need to focus a little bit more on it and ensure we're getting, a good solution there, but that's going to need more analysis. So continuing on, we took the difference in the average velocity magnitude now for delta. Oops. So this is same thing. Don't know why it's repeating this. Why is this thing changing on me? There we go. Sorry, something seems to be wrong here. So we did the same thing now, but this time going through and using the different time step sizes. So in this case, delta CF equals 0.01, and then taking the difference between CFL equals 10 and 1 and 101. And again, the largest differences are in separated flow, but we do see now the differences extend to the attached flow. So in this case, you can see some differences in the boundary layer over the front end of the vehicle. Now, these increased differences compared to the convergence, in this case, it's up to 13% of the free stream for CFL equals 10 and 43% for CFL equals 100 versus the 8% we saw before. So our key takeaway, there's a better match in the flow with smaller time step size and fewer inner iterations than the larger time step size with more inner iterations. So this aligns with what we saw previously for the force coefficients as well. Now, when we go through and take the design trends, in this case, just again, taking the difference between case 2A and 2B for CFL equals 1 and looking at our different convergence criteria, we see the design trend for delta CF equals 0.1 counts doesn't match our best resolved case up top. Again, I want to bring up that's likely due to that numerical issue we saw before. But if we go through and look at delta CF equals 1, we do see a similar design trend. Now, there is a clear reduction in the details for the wake and underbody flows, indicating that we're not getting, quite as good resolution there. And that actually aligns with what we saw with the vehicle forces, where again, that one count delta CF started to break down our design trend before. So if we now go over and take a look at it for CFL equals 10, what we see is this time delta CF equals 0.1. This aligns with our best resolved case. We see a very similar trend between those two. And again, when we get to delta CF equals 1, we start to see a breakdown in that design trend, again, aligning with what we saw before for our force coefficients. So now we do want to see, though, how do these design trends compare to each other? Are we still getting the same thing for the different time step sizes? So we take a look at CFL equals 1 and 10. And again, the general design trends match. We do see a slight difference in the boundary layer over the upper surface of the vehicle, but overall the wake and underbody seem to show the same trend. So our key takeaway, we do get a better match in flow design trends with larger time step sizes and more inner iterations than a smaller time step size with fewer iterations. So that deviates when we're going through and considering a direct comparison of just a singular vehicle. So our key takeaways here. There's an increased sensitivity to inner iterations for vehicle forces and flow field with increasing time step size. Now there's a balance, though, of time step size and inner iterations that is dependent on the application of interest. If you're going through and trying to reduce costs for a single vehicle, smaller time step sizes with fewer inner iterations would seem to be the recommendation here. But if you're going through and looking at the design trends, you can actually relax that and use larger time step sizes as long as you have an increased number of inner iterations. So for future work, we want to continue our uncertainty analysis of the flow field. We also want to go through and compare the trends that we're getting with that uncertainty for time step and convergence, because then the question becomes, are these trends greater than the flow field uncertainty? Is this something that is just statistical noise, or is this something that is actually a meaningful trend? With that, I will stop now and take any questions from the audience.